The two cylinders in this problem are connected end to end. They each have the same length, L0, which is 3/4 of a meter, and they have the same diameter, 1.5 centimeters. From that diameter, we can calculate their cross-sectional area. That's pi r squared, or pi d squared over 4, which works out to 1.77 times 10 to the minus 4 square meters. One cylinder is steel, and the other is copper. We're told that 4,000 newtons of tensile force acts on each end of the cylinder, and we're asked to calculate in part A the strain and in part B the elongation of each cylinder. We'll solve part A using the definition of Young's modulus. Y equals the stress divided by the strain. Solve this equation for the strain, delta L over L0, to see that it equals the force over the cross-sectional area times Young's modulus, and substitute the known values. The Young's modulus for steel is 2.0 times 10 to the 11 pascals, or Newton per square meter. When you calculate, you find the strain is then 1.1 times 10 to the minus 4. That's a dimensionless number. It's the ratio of two lengths. Make the same calculation for the copper cylinder using copper's Young's modulus of 1.1 times 10 to the 11 pascals, or Newton per meter squared, and you find that its strain is 2.1 times 10 to the minus 4. Part B asks us to find the elongation. That's delta L. We know the strain for the steel and copper, and from that we can solve for delta L, the change in length, or elongation. That's just the strain multiplied by the original length L0. For the steel cylinder, this works out to 8.3 times 10 to the minus 5 meters. That's how far the steel cylinder stretched as the 4,000 newtons acted on it. Making the same calculation for the copper cylinder, we find that its elongation is 1.6 times 10 to the minus 4 meters. That's how far it stretched as the 4,000 newtons acted on it.